This screencast is on orbitals and electron configurations. At the end of the screencast, you should be able to predict electron configurations and how many electrons are in the outer valence shell of an element. Here's your periodic table that we like to use, or the black and white one. Please have one of these available for this screencast. The elements are arranged in blocks. The blocks represent energy subshells, and then there's an energy level 1, 2, 3, 4, 5, 6, 7, which would be periods, and it's all based on Bohr's model. The first energy level is 1, and if you look at the s block orbital, it can contain up to 2 electrons, 1 over here, plus the next one, which is helium. When we go to the next element, we have the first energy shell filled with 2 electrons, lithium here, and then the third electron goes to the next shell or energy level, and it fills the first slot in the s block. In addition to the s block, there's the p block orbital, which can contain up to 6 electrons over here in green. There's the d block orbital, which can contain up to 10 electrons in orange here. And then in purple, we have the F block orbital, which can contain up to a maximum of 14 electrons. Remember, each energy level can be represented by the periods, which are the rows here, and the S, P, D, and F blocks are subshells or sub-energy levels within each shell. Let's look at 2 elements here. The first one is hydrogen. The second one is neon. Take a look at your periodic table as you follow along. You'll note that the first element, which is hydrogen, is element number 1. It also has 1 electron when the atom is in a neutral state. In other words, it's not an ion. The same with neon. The atomic number is 10, which means it has 10 protons, and of course 10 electrons. And these electrons are arranged in 2 shells. The first shell has 2 electrons in it. The second shell has 8 electrons. And each shell, again, is an energy level. And what we're trying to do by looking at Bohr's model is determine valence electrons. So a valence electron is the number of electrons in the outer shell. If you look at hydrogen, it has 1 electron. The next element, helium, has 2 electrons. And then we drop down to the next period, lithium through neon. And at neon, we get 8 electrons in its outer shell, as represented by this diagram here. And it's a nice, stable element, as are all of the noble gases here in this reddish color. The way we track the electron configurations is as we start with the atomic number 1 through 10. We label them as 1s1, and that's the electron configuration for hydrogen. 1s2, that's the electron configuration for helium. In other words, you're in the first period, you're in the s sub level or subshell, and then there's 2 electrons in it. When we get to lithium, it goes down to 1s2, which is the first shell it fills. Then it fills the next shell, and it fills the s subshell right here with 1 electron. In other words, it'll have 1 electron in this outer valence shell, which is what this is here. Next, we can look at a 1s2 and a 2s2, which means this outer valence shell has 2 electrons, which is the s. And we all go all the way down here to neon, and we see that it has 8 electrons, and in its outer shell it has 2 plus 6, which is 8 total. And the electron configuration is 1s2, 2s2, 2p6. And this is how we can represent that, and here it is on the periodic table. We happen to have this color code here representing the block orbitals, and then of course the normal color for a halogen, which is a reddish orange here. Here's the 1s2, 2s2, 2p2, and it can also be abbreviated as helium He in blocks with just the second level associated with it, and then we just identify this helium element here to lead it off. And I'll show you more examples of that. Here's magnesium. Immediately for a shortcut, we go over to neon and say the electrons are like neon. Put neon in here, and then in the third shell, there's 2 electrons, so it's neon 3s2. And then over here we have mercury, which we have xenon, Xe. Then we come across here to 6s2. We go over here to 4f14. So we come all the way across here. There's 14 of them. And we go to 5d10. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the 10th one is down here, which I skipped. All these arrows is to remind you that there's an electron spin and an electron counterspin for each subshell. So one electron spins one way within the valence shell, the other one spins the other way within the shell, and so on. As you load these, first one here, so you have the spin, counterspin, then as you go into the next orbital, you load 1, 2, 3, which spin the same way, and then you load the other 3, 1, 2, 3. So that's all these arrows, and it's just designed as an instructional aid to help you through in determining orbitals. Here are the elements drawn with the electrons around them. And note here that in this outer shell, there is 2 plus 6. So it's a 2s2, 2p2, and that means there's 8 electrons in the outer shell. If you look over here at magnesium, there are 2 electrons in the 3s shell, and then everything else is like neon, which is this element here. And we go to a more complex element, mercury, which has 80 electrons. It's hard to actually even draw or view with 80 electrons. It's quite busy. And that we notice that the outer shell is a little harder to determine as you get down here, and we don't normally work a lot with these in this class, but there is actually 2 electrons in this outer shell because this is a 6s2, and that's the highest energy level. These subshells here get a little bit more complex in how they load. There are some exceptions, and we'll talk about those in a minute. Here's how we can check our work. We can go over to Wolfram, we can type in neon electron configuration, and we'll get the results for helium plus the electron configuration, exactly as we just got. We can do the same for magnesium and the same for mercury. There are some exceptions to Bohr's model. If you take a look here, instead of fluorescent magenta color, we have a blue color. Like for example here at chromium and copper, we have 3D. And that just means that this element doesn't really follow Bohr's model. And if you look it up, you'll get something different than what you might expect right here, or for silver right here. Let's take a look at that. For copper, you actually get a result if you go to Wolfram alpha of a 4s1 3d10. That just means that instead of loading the electrons as Bohr's model predicts, it loads them in a different subshell of a higher energy level first and places them a little bit out of order here. So that's what this blue represents. This is the actual configuration. This is what Bohr's model predicts. Of course, we're going to use this in class. That's just fine for class. The same can be said of silver. It loads the electrons a little bit out of order as you go into these outer shells. As you get more and more shells, more energy levels, the electrons behave just a little bit different, and maybe a little bit surprisingly. So this is what we expect with Bohr's model, and then this is what we would expect in reality. Here's our image of the block orbitals and all the spins associated with it. All you need to do is just read from left to right and remember that this D block orbital here starts with a 3D, and then this one is also offset by 1, so it goes a 4F, then it goes to 5D. And you can just put these in this order. The order is somewhat controversial. It's just as an aid to help you determine orbitals. And back to your periodic table, you can easily see that the block diagram we just saw, let's go back to it, translates real nice to the periodic table here with the metals. Thank you for watching this screencast.